Okay, science time. We're going to talk today about hopefully I will be able to keep this brief. We're just going to call this the gas laws. And we usually agree upon, depending on what you define as a gas law, somewhere between 3 and 5 gas laws. We're only going to talk about 2 of them today. We will talk about all 3 of them, but we're only going to do math with 2 of them. Actually, I don't know. That may not be true. They're not complicated. And this worksheet that I'm going to give you is only about what's called Boyle's law and Charles' law. So we're going to talk about those. First of all, the gas laws. We're talking probably about what state of matter here? Gas. And in all of these, in the gas laws, we relate pressure, volume, and temperature. There's another gas law called the ideal gas law that also contains molar mass or moles amount of a substance. But the 3 that we're going to deal with today are only these ones. Let's define those things real quick. Pressure is what? As it relates to a gas, what do you think pressure is? We learned it last. Yeah, force per. Yeah, we would say, you say unit of area, because you're talking about square inches, which is fine. I don't love that unit, but force, which is measured in newtons, per, what does per indicate? What mathematical operation? Dividing. Force per unit of, area. And we usually measure area in meters squared, and that gives us the unit pascals. Volume? What's volume? That should be pretty simple. We should know this. How do we define volume in science? The equation is length times width times height. You're right, and let's put that, length times width times height. But let's also put how much space an object occupies. And this is important remember we had talked about Pascal's principle and Archimedes' principle, and this was important in them. Pressure was important in Pascal's principle. And then temperature, we know, we could simply define it to an elementary school student or someone who isn't very well educated as how hot or cold something is. But let's put, since we know about the kinetic molecular theory, let's put the temperature is a measure of the average energy of particles in an object. What particles am I probably talking about? Sand? What particles make up an object? Atoms or molecules, whatever the unit of that, the base particle, the representative particle we say. A measure of the average energy of particles in an object. And we knew all those things. Those all should be review. But now we're going to just relate them together. So we start with something called Boyle's law. Boyle's law. And Boyle's law relates pressure and volume are related by Boyle's law. Think about it just conceptually. If I increase the pressure I exert on a balloon, we're going to use a balloon for all these examples, because why a balloon? Yeah, because it's a container of gas, and it's movable. Remember, gases are not what we call incompressible. Fluids or liquids are incompressible. We talked about that when we talked about hydraulics. But in Boyle's law, we're going to relate the pressure and the volume of gas in perhaps a balloon. If I increase the pressure on a gas, if I push really hard on the balloon, since balloons, gases are compressible, what's going to happen to the volume? Yeah, it's going to contract. It's going to shrink. So we relate them in this way. So what we call those what? If the pressure goes up, the volume goes down. What kind of proportional is that? Do you remember? Inversely proportional. So pressure and volume of a gas are inversely proportional. The equation for this is this. P1 V1 equals P2 V2. The 1 and the 2, what do those probably represent? The P and the V probably represent what? Let's just start there. Pressure and volume. And then the 1 and the 2 represent probably what? Well, there's another way we could say it. We have 1 and 2, but we could also have what? We could have 2 and 3. We could have final and initial, or we could have before and after. It's how it changes. So before, when the balloon's just sitting here, it has a certain pressure on it, and it takes up a certain volume. And then I increase the pressure. Now I have a higher pressure, and the volume must get smaller. Think about it this way. If I have just very simply, we're going to use units, but if I have 2 times 2 over here, certain pressure, we'll say 2, pressure of 2 is pushing on the balloon, and it has a volume of 2. If I then increase the pressure to 4, what must the volume be to make this equation work? No. No. If 2 times 2 is over here, 4 times what goes here? 1. 1. So the volume did what? From 2 to 1, it went down. Yeah, it decreased. So the pressure went up, the volume went down, it decreased. Okay? When we actually go to solve these, what am I always going to have? Every single time I need to write it down, right? That's step 1. What am I always going to have to do when I solve these? Every single time. We don't always do it all the time with every equation, but with these I'm always going to have to what? Manipulate. How can you tell I'm always going to have to manipulate? Yeah, because there's never only one thing on either side when we start out. Every single time we're going to have to manipulate because both sides have 2 things on them when we start. Do you see? So like if I'm solving for pressure 2, I need to divide volume 2 over. Does that make sense? Okay, we'll do an example of that. But first let's talk about Charles' law. Charles' law, oh, I'm going to do this in a different color. Ooh, that'll be fancy. You guys think that'll be fancy? Yeah, it will. Good. Good answer. Charles' law relates volume and temperature. Oh, I wrote the word volume, but I meant to write Charles. I don't know that that happens very often. Charles' law. Oops. I would put Charles and then an apostrophe afterward, because that's how I say it. I think that's how your book says it. If you would, if you're inclined to say Charles's, which is your book actually says Charles's, that's fine. You just put another S afterward. I would say Charles. It doesn't really matter. What I'm trying to get at is that words that end in S, sometimes we put the apostrophe afterward and it's still possessive. Charles' law. This is the law of Charles anyhow. So this one, we're relating volume and temperature. You know from your lab, what happens if I increase the temperature of a gas? The volume, it gets hotter. Thank you, Cyrus. That's very good. But also, it expands. The volume gets larger. So are volume and temperature inversely proportional, like pressure and volume were? No, they are. Yeah, they're directly proportional. Directly proportional. It's all wrong. Volume and temperature. What does that mean will happen if I decrease the temperature? Mm-hmm. Did you find that too? Yeah, in the freezer. When we put the balloon in the freezer, it got smaller. Volume and temperature of a gas are directly proportional. So what do you think the equation for this is? If they were inversely proportional and we multiplied P1 by V1 equals P2 times V2, what do you think we're going to do if they're directly proportional? Divide. And the division is V1 over T1 equals V2 over T2. You're going to be extremely careful with this one. Why? Yeah, because you're dividing. So you're still every single time going to have to manipulate. But what if I'm trying to solve for T1? What do I have to do first? Careful. I have to get T1 over here first in the numerator. There are other ways to do it, but I'm insisting that you do it this way. Multiply both sides by T1 and then divide the other stuff over. Okay? Charles's law. And then there's another one that's not on your worksheet, but we're going to talk about it. I think your book leaves this out because it has a funny name. The man's name is Gay-Lussac. But this one relates, if Boyle's law was pressure and volume, and Charles' law was volume and temperature, what do you think Gay-Lussac's law is? Yeah, temperature and pressure. Temperature and pressure is Gay-Lussac's law. And the example of this, and like I said, this is not in your book, it won't be on the test, and it's not on your worksheet, and it's not in the chapter review. We will do it when you're in chemistry, and there is math for it, but in order to expedite things, I'll just describe it to you. What it is like if you ever use the canned air to spray out a keyboard or something, or you ever grill. Have you ever grilled anything at like a propane grill? Or maybe you notice, maybe your house has propane heat. Well, as the pressure in the propane or the compressed air goes down, as the pressure decreases, as the stuff is leaving, propane's leaving the tank to go in the grill, or propane's leaving your tank at your house to go into the house, or the air is leaving the can, as the pressure is decreased, the temperature goes down. That's why if you spray the compressed air, especially if you hold it upside down, it is freezing cold. The temperature has decreased a lot because the pressure has decreased. That's also why the other way is why when you see a asteroid or a piece of a spaceship come into Earth's atmosphere, people think that's friction that makes it so hot. That is not true. What it is that it's going so fast that the air pressure builds up in front of it, and an increase in pressure makes it what? If a decrease in pressure made it colder, an increase in pressure makes it hot, really hot, in fact. That's also why if you pump up a bicycle tire with the hand pump, you ever do that? The cylinder will get extremely hot, and people think that's from friction too, but it isn't. It's because anytime you increase pressure, it generates heat. It increases heat. That's Gay-Lussac's law. Okay? So it is that temperature and pressure are directly proportional. Yes? A gun is also having a chemical reaction that generates heat too. But yes, to some extent there is, and we call that adiabatic heating. To some extent there is heating because of pressure. I'm certain there is. But a lot of the heat is probably because of the chemical reaction that's occurring there. Do you have questions about any of these? We will do a couple math problems here, but do you have questions conceptually before we go on? Peyton? Jaden? Okay, I'm going to erase all this. Okay, so what I want you to write down, you don't have to write down the problem, and I might not even write it down, but we are going to write down all the work that goes with it, okay? So we're going to say, let's say a temperature of a balloon is, here, let me give you a little, this is not just cheat code, this is the rule. Temperatures for this, all temperatures, the pressures and the volumes can be in whatever unit you need them to be, but the temperatures must be in Kelvin. They have to be. Have you heard of Kelvin temperatures before? Yeah, we talked about them before, is that right? Or did we talk about them last year? Okay. What is the Kelvin temperature scale like? Why do you think we have to use Kelvin? That's a nice reason, but we could use Celsius for that. We could use Fahrenheit. Everyone in the world is relatively comfortable. We could do either of those, except that in the Kelvin scale, what's nice about it is where does it start? 0 is what in Kelvin? It's absolute 0, which means that the universe cannot be colder than 0 Kelvin. Why would that be handy for us? Yeah, you can't go below 0. There's no negative numbers, because if you use a temperature scale like Celsius or Fahrenheit that does have negatives, and you use a negative temperature, you'll come out with a negative mass or a negative volume, and neither of those things can exist. There's no such thing as negative mass or volume, so you have to use Kelvin. So here's the rule. If we have degrees Celsius, we need to subtract 273.15 Kelvin to give us a Kelvin temperature. And if we have Kelvin and we need to go to Celsius, which will happen, because sometimes it'll say, find the answer in degrees Celsius. And even though we have to do the work in Kelvin, we need the answer to be in degrees Celsius. So Kelvin plus 273.15 is Celsius. And it's just as easy as that. You just add or subtract. Remember, though, that the Kelvin temperature scale, there is no 0. So you're always adding if you have kelvins. So the temperatures must be in kelvins. But let's say we have a gas that we increase the temperature from T1 equals 293 Kelvin, T2 equals 315 Kelvin. Volume 1, the original volume was 1.1 liter of gas, and we want to find volume 2. Okay? So far, so good. Can you imagine that a question might say this? Yeah. Do you have kind of a little plan in your head as how you might solve it? First step. And what equation would we use for this? Well, we look at our variables. Is it always going to be this easy to just see the variables right here lined up in the side? No. In fact, most of this worksheet, I'll show you the worksheet. Most of the worksheet is probably what? No, I wouldn't call it vocab. Most of the worksheet is, yeah, they're word problems. And so we're going to have to kind of tease out from the worksheet what is temperature 1, what is temperature 2, and well, first of all, how do we tell in language, in our story problem, which one is temperature 1 and which one is temperature 2? It won't say that in the story problem. It'll say, yeah, it'll say the initial temperature of a balloon, or it'll say the temperature went from, and if it went from blah, 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 to, if you went from X to Y, then X is T1 and Y is T2. Do you see what I mean? So it's always, you have to be able to tell from the story problem which thing is which. That's going to be your main problem. Anyway, what isn't going to be a problem, because you already know how to do this, is what? What's step 1? Raw equation. What is the raw equation here? You do have to have these memorized, so let's get on that right away. V1 over T1 equals V2 over T2. What must I do? Every single time for these, I need to manipulate. What am I trying to solve? Volume 2. So what do I need to do to get it so that volume 2 is by itself? Colton? Well, look at it. What do I need to do to get it by itself? Okay, well, you could still answer my question. Someone else. What do I need to get volume 2 by itself? By T2. That'll make these T2s reduce to 1, and now over here we have T2 V1 over T1, so that's supposed to be a T, equals V2. Why didn't I just put my numbers in? Always, always, always manipulate before you substitute. It really confuses you. You don't think it does. I'm smarter than that. You're not. Always, always manipulate and then substitute. Okay, so now let's substitute. What's temperature 2? Well, we had over here, temperature 2 was 315 Kelvin. Volume 1 was 1.1 liter. Temperature 1 was 293 Kelvin. How will I type this in my calculator? Well, I would type in 315 times, you'll be able to use the calculators we have here, 315 times 1.1, enter, and then divided by 293. Why press enter? Because what's going to happen if you press the divided by, it's just going to straight up divide 1.1 by 293, and then it's going to multiply that into by 350, which may work. I don't actually know. But at some point it won't. I've had it mess up before. So I always do multiplication in one step, then divide by each individual thing that needs to be divided. Okay, answer? He can't grab it. Someone help. He has no, he can barely use any of his limbs. Tatum, please be nice to the calculators. It's not their fault you guys were not paying attention. So I'm going to type in 315, 315, multiplication sign, 1.1, enter, divide by 293. Units are the most important thing here, but you don't put them in your calculator. So what is it?
I got 1.18.
1.18 liters. Did the volume go up or down? Let's try again. Did the volume go up or down? The volume went up. It went from 1.10 to 1.18. Does that make sense for what we just learned about? If the temperature increased, does it make sense for the volume to have increased? It should. That is the right answer. Okay, new one. New one. This time, let's all pay attention. What? Hey, by the way, what law was that? That was Charles's law. The way you can remember, this is honestly how I remember them. I think about boiling relates to temperature. And Boyle's law does not have temperature in it. That's how I remember. Boyle's law does not have temperature. So just remember that. Okay. Let's do, speaking of Boyle's law, let's do one now where, let's say that the pressure exerted on a balloon is 1.33 atmosphere. And it starts out with a volume of 4.2 liters. The pressure is decreased to 0.98 atmospheres. What is the new volume? Step 1. Good. What is the raw equation for this one, and how do you know? Which one are we going to use is what I'm trying to ask. Oh, sorry, this should say 2. This should say 2. I'm going to use Boyle's law, which does not have temperature in it. Good. Now what must I do? Peyton? Mm-hmm. Yep, divide by P2. So I end up with P1 V1 over P2 equals V2. Next step. Jaden? Substitute. Good. What should I put in? Tell me exactly what to write. Are you having a hard time seeing over here? I'll ask Tatum. Tatum, what should I write in here? Oops. Oops. You have to have the units. 1.33 atmospheres, which is a unit of pressure. Sorry, go ahead. I prefer, this is a personal preference, but I prefer to show my multiplication by a parenthetical expression like this instead of, I really don't like an x. Please don't use an x. I mean, I'm not gonna come to your house and burn it down if you use an x, but if you can help it, try to use an x. A dot is okay, except for the problem with a dot is that there's a specific thing in physics and engineering called a dot product, which is not the same thing as just multiplication. So I really prefer just to show the two numbers next to each other in parentheses. Anyway. You did. 570? That, I'm not saying it's necessarily wrong, but I would be surprised if it were right. 1.33 times 4.2, enter, divide by 0.98. There, I think that's more like it. I think you probably forgot, yeah. 5 point, what was it? Okay, 5.7 what? Well, atmospheres drop out, we're left with liters. Basically, what kind of mathematical operation are we doing here without specifically calling it that? These are whats? You remember from junior high? There are variables, but what I'm talking about, these are proportions. All they are is proportions. Basically, 1.33 relates to 4.2 as 0.98 relates to what? They're just proportions. They're just a special way of doing proportions. Do you have questions? Do you think you can do these? Okay. Oh, on the video I'm going to assign, the chapter review is page 500, 1 through 24, which is all of them. I could just write page 500. Page 500, 1 through 24, and then there's also a worksheet. So page 500, 1 through 24, plus gas laws worksheet. Well, hey, and also on the video, why do I assign you a worksheet? Just to be a jerk, right, Colton? No. Why do I assign you a worksheet? Someone make something up at least.
So you know that we are prepared for our test?
No, a little bit. No, a little bit, Colton. I have to make sure that you actually know how to do this. So a little bit checking up on you. Yeah, but that's not the main reason. That's 10% of the reason. What's 90% of the reason? You should have a higher opinion of me than this. No, I don't care about that at all. No, I don't care about that at all either. Come on, you can have a slightly higher opinion of me. Yes, because you need what? You need practice. You can't learn to ride a bike if you don't practice it. This is due because of that, because I don't hate you, Colton, and want you to stay up all night doing it. It is due, let's say, Wednesday. You'll have all day in class tomorrow to work on it. I do want you to have the time you need, and I want to be able to be there when you're working on it. What, Colton? Yeah, okay, whatever. It's due the 19th. You should say thank you instead of being a jerk. Jaden, could you say thank you? Say thank you. You're welcome, Jaden. Okay, now listen. That was all a fun joke, but in all honesty, I do want to be here when you're doing them, so you have time the rest of class today to work, and then you'll have all day tomorrow to work on these things because you need to practice, because it is important. Even, listen, homies, let me give you a real truth. This is not going to come up in your life, probably. Unless, if you're going to be an engineer, it actually will, because this is really very common in engineering. But, okay, so why do you need it, Tatum wonders? What is beneficial about that at all to you? Okay, you'll never use this, but you will use this exact kind of problem solving. I promise you, you have to use this kind of problem solving. Colin's rolling his eyes because he doesn't believe me. But let me tell you, you're not going to use this, but if you can do this, you can pretty much do anything. If you can sit down and shut up and do your work, you will be able to do work. It doesn't matter if you're going to be rancher or police officer or president or engineer or Arby's employee for your entire life just growing zits for a living. Any of that is fine. You will need to problem solve, and this is going to help you, I promise you. And I truly believe that. I don't care about having to put a grade in the grade book. I don't care about checking up on if you've done it. I do care that you have gotten the problem solving skills that you need to be a successful person, which you don't have yet. I know you personally. Bye.